My name is Nomar González-Santini. I am attending the SROP 2013 at the University of Michigan. I am studying electrical engineering at the University of Puerto Rico at Mayagüez. And right now I am working with Professor Juan Rivas at the Power Electronic Lab. The objectives of my project were to test the gate drive circuit of a class 5 resonant inverter to generate very high frequency pulse width modulation signal to derive the switching semiconductor we were using, an ion channel MOSFET. Also, I have to derive a faster and more accurate method to model the static and dynamic characteristic of switching semiconductors in simulation. Before explaining what I did, I would like to give you a brief background about the project of my research group. My group is designing and implementing a high-frequency switching power converter. Based on a 5-2 resonant inverter, which shows a great potential for DC to DC application. Some of the advantages of working at high frequencies are the reduction of passive energy storage components, for example, the inductors and capacitors, and the significant increase in the dynamic response to compensate for fast load changes. This leads to applications in electrostatic control of microelectromechanical system devices, radio frequency power amplifiers, and induction heating. The following scene shows an example of induction heating using one of the inverters my research group did. As you can see, that little circuit is very powerful. Now, it is time to talk about my actual work for this project. The first task I did was the testing of the MOSFET gate drive circuit. The gate drive plays an important role in the inverter because it is the one that makes the transistor switch between on and off at 13.56 MHz, so making the converter work. Therefore, we need to have a good driving signal to ensure appropriate functionality of the converter. Here is a flowchart that shows the procedure that I used to test, find the problem, and fix the gate drive circuit. First, I used the oscilloscope to study the signals in different points around the circuit. The following are the problems I found during testing. Short circuits due to bad soldering, missing and/or damaged components, components collocated in a wrong position. The only way to fix those problems was by soldering. The following scene shows an example of the process I did for the soldering. After soldering, I had to test the gate drive again to see if I solved the problem. If I did not fix the problem, I have to repeat the whole process again. If I fix it, I should obtain the waveform shown in the following scene. Notice that the frequency is 13.56 MHz as expected. This proved that the problem was fixed. My second task was to model the switching semiconductor. The design of efficient converters switching at tens of megahertz relies heavily on the modeling of the static and dynamic characteristic of switching semiconductors. At those frequencies, considering the switching semiconductor as an ideal switch on simulations will be really far from reality, making a huge difference between the simulation and real case scenario. Therefore, we have to take in consideration the parasitic components, because at high frequencies the behavior of such components deviates from the idealized model. Reason why, for this project, it was necessary to measure the nonlinear device capacitances and conduction characteristics of a high-performance MOSFET using a power device analyzer. By doing this, we have developed a fast modeling strategy based on experimental data. Previous simulation models have relied on models derived using a time-consuming process that involves curve fitting data obtained from the manufacturer datasheet, as shown in this video. Models based on experimental data, but used more equipment than the method I am going to present, that only uses the power device analyzer. It was less automated, so it increased the probabilities of having a mistake writing the data, while in the new method you get the data directly from the machine. On the other hand, it can take more than a day to get the data, while the new method can take just seconds. It had less resolution and less power capability than the new method, that can have more than 1,000 data points and can reach high power measurements. Here is a flowchart that shows the procedure I used to model the switching semiconductor. The following scene shows an example of how I took the measurements for the new approach. Once I have the measurements, I have to import this data to MATLAB. This is to compare the experimental waveforms with the datasheet. This is an example of one of those comparisons. As you can see, there is a variation between the experimental measurements and the data obtained from the datasheet. That variation can make huge differences between the simulation and real behavior of the inverter, especially working at such high frequencies. Again, this is the reason why we want to do the modeling based on experimental measurements. Once I compare the waveforms, I'll build up the MOSFET simulation model in AutoSpice, and then I verify the matching between measurements and simulation to see if I obtain the right behavior of the MOSFET. Once I made sure that everything was okay, I used the MOSFET model in the converter simulation. In conclusion, careful placement of small surface mount components is needed to provide the correct functionality and generate the appropriate signals to drive the switching semiconductor. The new method to model the electrical properties of the switching semiconductor allows faster modeling, with more data and more accurateness compared to the previous method. Part of the future work includes the evaluation of the accuracy of modeling the switching semiconductor with the power device analyzer and automates exporting the data from MATLAB to AutoSpice. So, that was my project about. Hope you enjoy it and learn from it as I did through the summer.